presenting this. I'm excited to be presenting this work, which I did starting as a PhD student at New York University with my advisor, Jonathan Weir. John and I are basically mathematicians, but we really like developing numerical algorithms and applying them with the help of subject area specialists. So our help for this project came from Dorian Abbott in geophysics and Sam Hayden, who's in astrophysics. This is work about rare event sampling in the Earth and planetary sciences. And the talk, bam, okay, is organized with mathematical detail in the first part. So I'm going to take you through a mathematical example in which we can discover everything that we possibly want to know about rare event sampling. And then I'm going to talk about how to make it practical. And we'll talk about heat waves in Europe, about hurricanes in the US, and about solar system collisions. So there's going to be a lot of terrible and fascinating events that get simulated on a computer. And that's really exciting and potentially also informative about how these systems work. And then, as not to present too rosy a picture, I will share some ongoing challenges, some reasons that applications of these methods remain a little bit hard. And we're trying to make it easier every day. So, background. We want to use high-resolution Earth and planetary models to simulate rare events. And I'm sure you all know about this. Higher resolution, a shorter time step, more grid points usually leads to better models. But the problem then is running a model can take months and thousands of CPUs. The sky is the limit. And a 1 in a million event would require at least 1 million model runs, maybe more, maybe 10 million model runs to get an idea about how frequently it occurs and what it looks like when it does occur. So whatever can we do? Rare event sampling is a whole slew of methods that push the limits of the rarest events that scientists can study. And so the 3 examples that I'll be talking about are heat waves in Europe, hurricanes in the US, and solar system collisions. These are early pilot demonstrations of how powerful rare event sampling can potentially be. Now, our motivation, the motivation of me and my co-workers, is that rare event sampling can be pushed even further. We still think that we can push it to new, higher resolution models to rarer events. But first, its limitations need to be seriously addressed, which are algorithms are hard to set up and require some fine-tuning of parameters currently. And then also the limits of applicability, the fundamental limits, remain a little bit unclear. So there's practical opportunities, there's theoretical opportunities. It's an exciting research area. We think that as the next frontier for computation in the Earth and planetary sciences, we are trying to understand and improve rare event sampling. That's what we're doing. Here's a picture, just to give you something visual to grab onto. This is Hurricane Katrina. We want to simulate events like Hurricane Katrina, but of course we need a good model. You can see this is the Earth and this is a hurricane. The eye of the storm has extremely intense winds and pressures. The eye of the storm is also really small. So ideally you would want high resolution, like less than or equal to 1 kilometer grid boxes, ideally. And that would be a very expensive simulation indeed. What we ideally want would be some cleverly designed Monte Carlo rare event sampling scheme that is as accurate as direct sampling with 1 million samples, yet as cheap as direct sampling with just 1,000 samples. Wouldn't that be nice? We also want it to be simple to use, which specifically would mean in the Earth and planetary science context that it only requires running a model forward and that the parameter tuning is pretty easy. So you only have to do it once, maybe after a couple pilot runs. So these are the desiderata. And what's probably the best potential solution is splitting and killing, which I am illustrating in a schematic on the right. The black dots are indicating that a trajectory is continued forward in time and potentially split into multiple child trajectories, which means that some random seed is changed, so they'll have different stochastic evolutions, but they're starting from the same point. So you just get split into 3 kids, and then you all develop into your own unique human beings with your own interests. That's sort of how it works. The white circles indicate that a trajectory is killed. It is discontinued. And this would be a mean zero process. The simulations would want to have a position that's centered around 0, but through splitting and killing, we are ratcheting the events towards higher and higher positions, and we are reaching some high positions indeed, like x equals 3. So this is the idea, a schematic idea, and it'll become more and more practical throughout the talk. Now, to start with the math, I want y'all to consider an idealized example, and then we're going to adapt it to real-world applications later. The idealized example is called an Ornstein-Uhlenbeck process, or an OU process. It's a nice example because the stationary density is a normal random variable with mean 0 and variance 1. So it likes to stick around this normal density over time if you look at its time averages. And it's driven by these dynamic equations. There's a mean reversion term, which brings you back to the origin, and then there's some Brownian motion forcing. We want to calculate a crazy quantity, the expected value of e to the 4x1. So that's the 4th exponential moment. That's going to be really, really, really large when x1 is large at time 1. We want to calculate this crazy quantity using only 1,000 samples. This is going to be the idealized math example. If you were to draw just 1,000 OU trajectories without any splitting and killing, indeed, they would hover around 0 with a standard deviation of 1. These are 1,000 trajectories with some opacity, so you can kind of see where most of the density is. This might seem a little bit weird, this example, but let me try to convince you it's not, and let me try to convince you it's hard and important. So why is it even a hard problem, first of all? I mean, it's a hard problem because we need to evaluate this integral, e to the 4x pi x. And to evaluate an integral, you need to sample the critical region where the integrand is the largest. And where is that? That's crazy high. That's centered at 4 and maybe has some high values around 3, some high values around 5. And if we were just to draw 1,000 OU trajectories, we would never really get to that critical region. We would maybe see it with 1 sample or no samples at all. This is a little like calculating the expected damage from a hurricane. The greatest contribution comes from something that doesn't happen very regularly, but is so exponentially destructive. And that would be a category 4 or 5 storm hitting a major city. So think of this e to the 4x just as the exponential damages due to some hurricane, which could be big, could be small, but we really care about the high intensity events. Diffusion Monte Carlo, which can be traced back to the father of computing sciences, von Neumann, back in the 1940s, is a rare event sampling scheme that repeats steps of evolution, measurement, and splitting and killing as follows. Evolution, run the model forward. That means you advance from the current state to a new state and do it with 1,000 different simulations, n equals 1,000. Measurement, evaluate what is called a reaction coordinate for each of these simulations that measures progress toward the rare event. Are you making progress in getting to that critical region or not? It's called a reaction coordinate because of connections with chemistry, where this was used to study chemical reactions and whether they would occur or not occur. but we're going to extend it to the Earth and planetary sciences. Splitting and killing, you randomly sample a new ensemble, starting from the existing states with importance weights, and the importance weights are what's critical. At the first time, the importance weight is just your reaction coordinate value. So are you really high? You're going to have a lot of kids. If theta is really high, you're going to have a lot of kids. If theta is comparatively low, you might randomly die. It might be a killing event. At subsequent time steps, it's going to be the ratio of your new reaction coordinate value divided by your old reaction coordinate value. So like, are you gaining in the reaction coordinate, then you'll have more kids. Are you losing in the reaction coordinate, you'll have fewer kids and maybe die. Here are some times. There's a reason for picking them. You'll find it out later. Simulate. This is the first round of evolution. Apply killing and splitting. Simulate. Killing and splitting. Simulate. Killing and splitting. Simulate. Killing and splitting. Simulate. And that's it. You have coerced your samples to go to a region they would not normally go to. This critical region, you can back out unbiased estimates of the quantity that you were trying to estimate in the first place. And these estimates have a little bit of a funky form, but what they're essentially doing is they're looking at the product of 5 different trajectory averages over your ensemble. So at the first resampling time, you would evaluate the average reaction coordinate value. It would be 5.06. At the second resampling time, you would evaluate the average ratio of reaction coordinate values. It'd be 4.61. At the third resampling time, the same evaluation leads to 4.91, 4.23. And then lastly, you look at the average ratio of e to the 4x1 divided by the previous reaction coordinate value. You get out an unbiased estimator. So not only is it unbiased, it's really good. It's very, very accurate. With 10 to the 3 samples, DMC, diffusion Monte Carlo, the scheme I just showed, is accurate up to plus or minus 35% relative error. So most of the time, you're going to get the first significant digit correct. Compared to direct sampling, with 10 to the 6 samples, with 1 million samples, direct sampling would do much worse. It would only be accurate up to plus or minus 298% relative error, which means you might have a quantity that is 4 times too large. You might be anticipating that the hurricane comes and does 1 billion damage on expectation. But in fact, in expectation, it only does $250 million of damage. You could be horribly off. Now, I was able to give you these precise figures for this mathematical example because it is the only one I know where the mathematics works out perfectly. I was working on it as a PhD student, and I was able to prove that the optimal, the lowest variance splitting and killing scheme for the OU process for calculating an exponential moment uses exactly the resampling times I chose, uses exactly the reaction coordinate I chose. The estimates are unbiased. The estimates have a relative variance that's given by a nice formula. And the big takeaway here, I mean, there's a lot of sort of precise mathematics, but the big takeaway is that if you're trying to estimate these exponential moments, e to the cx1, direct sampling, you would need order e to the c squared samples. So that's outrageous, you know, if c is 4, it's e to the 16, which is a big thing. I don't even know how big. It's, you know, larger than 1 million, right? But DMC needs far fewer. It needs order c squared samples and order c squared for sampling times. And this means, in a specific mathematical sense, hey, Kathy.
Can I ask a question?
Yeah, sure.
So it seems like what you're really doing is you're thinking about the covariance of the evolution of your algorithm. And that's an underlying thing in the way you're doing the sampling. Is that the correct way of thinking about it?
covariance of the evolution of our samples.
Well, so if you just did a direct sampling, you just go randomly in space and you would have no protection against going back to the origin.
That's right,
But what you're saying is preferentially go further away from the origin.
for sure.
And there has to be a mechanism by which you are evaluating that, which basically says, I don't want to be similar, I don't want to be going backwards.
Exactly.
You're programming that into your diffusion algorithm.
Yeah, that's right. That's right. It's a
So I
way
think
of
that as
correlating.
covariance between, I'm thinking of that as being covariance between adjacent samples.
Sure. It is surely covariance between adjacent samples. You know, you get this peculiar feature where a lot of the samples you see at the endpoint shared some ancestral lineage. You might see 100 great grandkids who could all be traced back to one particular Adam or Eve simulation, right? And so it's very correlated, but yet very accurate. One might think the correlations have to lead to inaccuracies, but not so. Not so for this example. This example shows that we can solve, in a sense, in a mathematical sense, exponentially hard problems at either linear or quadratic cost. Yes?
Maybe just to
Yeah, please.
back on Kathy's question. This is true for this particular reaction coordinate, which forces your simulations to go away from the origin. And
Yes.
That's how you get that covariance.
Mhm.
And if you choose it differently, you could get arbitrarily bad results too.
Yeah, you can do a lot worse than direct sampling.
Yeah. It's
Although,
all about a lot of it has to do with the choice of this reaction coordinate.
indeed, yeah. And that's going to be a major theme. I mean, I'm going to tell you all that the reaction coordinate's the most important parameter. That picking it means success or failure. I'm going to make a case that the other parameters are relatively easy to tune, actually, but the reaction coordinate remains challenging because that's what's driving the whole thing. And I'm largely going to do it through examples. So the rest of the talk is examples. And the first example wasn't us, but it was a hugely impactful study by Ragone, Wouters, and Boucher in Proceedings of the National Academy of Sciences in 2018. They're a European group who is interested not in hurricanes, because that wasn't really the local concern, but rather in heat waves, which can be hugely destructive in Europe, which can especially cause a lot of elderly folks or sick folks to die. So they were interested in how frequently, like what is the return time for a extreme heat wave, a sustained heat wave over a couple weeks to hit Europe. And they applied DMC. They used as their reaction coordinate, as this key parameter, the time averaged temperature. So just average the temperature anomaly from what it's supposed to be over a period of 2 weeks, and then use that as a reaction coordinate for predicting heat waves. Like a heat wave is already starting to develop, well, it's going to continue developing. Let's keep pushing it in that direction. They report 3 orders of magnitude speed up compared to direct sampling. And that's largely based on the plot to the right, where control means direct sampling. It means, you know, how much time can we afford on the model if we just run it forward without any splitting and killing. And they're giving estimates, which maybe aren't so great, up to about a return time of 10 to the 4 or 10 to the 3 years. They're running the algorithm and they're getting estimates of more extreme return times for more extreme heat waves, up to 10 to the 7 years. Now, this is a little crazy, obviously, because we expect climate change to move the needle by, you know, plus or minus 1 or 2 Kelvin. So this has to be interpreted as stationary climate conditions. You know, if we were to cease global warming right now, then how frequent would these heat waves be? But, you know, we expect all of these return times probably to be significantly shorter under current climate change situations. This motivated our group to try to understand what were they doing and how can we improve their method. And to go into the details of their method, they were using a climate model called PLASM. Have you guys ever used PLASM? Well, it looks like the figure to the right. It's got a rather coarse resolution, 300 kilometers per grid box, and 10 vertical levels. So, okay, I mean, they're developing a new method and they're using a model that's relatively computationally cheap next to the weather and climate models that I've used personally and that I expect many of you have seen or heard about or used. How do they make it stochastic? You need random evolutions. They added very small random perturbations to the surface pressure field, smooth perturbations, every 8 days. And this can be seen as some unresolved degrees of freedom. You have maybe some kinetic energy that's bubbling up from the fine scales to the coarse scales. I think that adding small random perturbations to a climate or weather model is something that can be well justified by random shocks from a lot of unresolved degrees of freedom and is an eminently sensible thing to do. So that makes sense. They simulated 512 samples for 800 days. So they weren't running the model for too long, but 800 days in perpetual summer conditions, I should add, in perpetual summer conditions. The one thing that really was tricky about their method is they messed around with this reaction coordinate quite a bit. They tried 4 different scalings for the reaction coordinate and then got a lot of estimates at the end and eliminated the outliers and did some smoothing over the remaining estimates. And in particular, if we want to improve this, if we want to make this a little bit more extensible and a little more useful to the Earth and planetary science community, well, first we want higher resolution models, right? Plasm is not really the bleeding edge by any means. And then also we want simpler parameter tuning. We don't want to have to try 4 different scalings. We want some simple procedure so that in principle, someone can run this once. Maybe with 1 or 2 pilot samples, they can launch their big ensemble of 512 samples just once and get the answer they want. So we invented a slight twist on DMC. This was some of my PhD work called quantile DMC as a more practical way to calculate rare event probabilities with simpler parameter tuning. So that was our simple goal, simplify. The main idea, this connects to the first part of the talk, is that we know how to apply splitting and killing to an Ornstein-Uhlenbeck process. We know the absolute best thing that you can do for an OU process. So let's use this knowledge to design a nice scheme. Assume that you have some reaction coordinate ZT that is actually a hidden OU process, and it's revealed through some monotonic transformation. It can be a time-varying monotonic transformation. Then what you can do is you can map your observations back onto an OU process using a quantile transform. Just like you can map any distribution that's one-dimensional onto any other distribution, just by mapping the 95th percentile member to the 95th percentile member, the 85th percentile member to the 85th percentile member, the 5th percentile member to the 5th percentile member. You can do this monotonic mapping and get back to something that's Gaussian distributed that we know how to deal with. And then just apply optimal splitting and killing to recover the optimal splitting and killing dynamics. So this will work for a lot more than just an OU process. It'll work for any monotonic time-varying transformation of an OU process. And maybe that's a much better idea for how to mathematically think about the reaction coordinates we're using in practice. It doesn't require so much parameter tuning. It's simpler. You need a reaction coordinate that identifies which samples are most likely to exhibit the rare event. And it doesn't matter how you scale it at all. It's literally going to be used to sort them. From you are the most likely to exhibit the rare event, you are second most likely, third, fourth, fifth, sixth, seventh, all the way to 512th. The target time when the rare event might occur, if it's a hurricane, for example, maybe we know it's going to hit the coastline on Thursday, so we're going to simulate until Thursday. That's when we think it might occur. That's when we want to concentrate our resources. the approximate rarity of the event in standard deviation units. Are we looking at a 3 sigma event or a 6 sigma event, a 9 sigma event or a 1 sigma event? And it's not especially sensitive. You can be off by 1 or 2 standard deviations, but you surely don't want to apply a 1 standard deviation algorithm to try to simulate a 12 standard deviation rare event. You wouldn't be splitting nearly enough. You would never see it happen once. Likewise, you wouldn't want to apply a 12 standard deviation algorithm to a 1 standard deviation event. You'd be completely oversplitting, and you would lose some statistical accuracy. Lastly, the decorrelation timescale for the system to lose its memory. So this is a timescale. For hurricanes, it's about 4 days. For planetary dynamics, it's more like 500 giga years. You can get it wrong by a factor of 2, and your algorithm will work fine, but you probably don't want to get it wrong by a factor of 10. Usually, we can estimate the target time approximate rarity and decorrelation timescale from just a few pilot runs. So maybe you run 2 or 5 or 10 samples just to get an idea of what the dynamics look like. However, identifying a reaction coordinate remains the most difficult part and crucial part of this algorithm, because the optimal reaction coordinate would be the probability of the rare event for the current state of the model. And that's like even harder to know than the overall probability of the rare event from the starting point. To actually evaluate the probability for all the ensemble members halfway into the simulations would be extremely tough. We need a proxy. We need a good proxy. And I'll give you examples of our quest to find good proxies for several different problems. Now, in this same paper where we introduced the method, we applied it to intense hurricanes. One intense hurricane in particular, Hurricane Earl. And we used historical starting and boundary conditions and just tried to figure out what's the chance that it could have developed with slightly different random evolution into a category 5 storm. Now, we produced with this algorithm several category 5 storms. Direct sampling produces none. And we mapped out a probability estimate of 0.002. So 0.2%. It's a 2 in 1,000 event. As our reaction coordinate, we use the minimum sea surface pressure. So if right now the storm has a really low minimum sea surface pressure, it's likely to be a very intense storm when it makes groundfall. With n equals 100 samples, we calculated probabilities that would have required 700 or more direct sampling runs. So in particular, this estimated probability of a Cat 5 storm, we were doing it 7 times more efficiently. And we couldn't have afforded 700 direct sampling runs, and I'll tell you why. I ran these simulations myself, and I used the WRF model, which has a wonderful feature of vortex following nested domains. And so this means usually there's 3 domains. And one covers like almost all of the Atlantic and a little bit of the eastern United States. And it's like 20 kilometers resolution, 18, I believe, because you want factors of 3. And then the middle domain is 6 kilometers resolution, and it's tracking the hurricane. Then right over the eye of the storm, I'm indicating the domain that is 2 kilometer resolution. So you have 3 different domains nested, one inside the other, like a Russian doll. And you're getting down nearly to that target that I mentioned of 1 kilometer resolution. You're not quite getting there, you're at 2 kilometer resolution, but this would still be regarded as a very good resolution by hurricane scientists, by tropical cyclone scientists. This would be a very serious simulation. And you can see that you're resolving the wind speed fairly well. You can see there's quite a few grid points right in the eye of the storm where there's not wind. And you're getting up to 120 knots. So you're resolving some very intense winds. For stochastic perturbations, WRF has some ingrown schemes. we used one called stochastic kinetic energy backscatter, SKED. And it creates kind of smooth perturbations to the non-divergent part of the wind field and also to the pressure field. Again, modeling kind of like subgrid scale random shocks to the system. We simulated 100 samples for 7 days. And each sample required a 48-hour runtime with every single core in a node. So I was taking up one whole node for 2 days. And I needed to run 100 samples. The University of Chicago had like 200 or 300 nodes at the time. And so I was able to get 100 nodes, which was really lucky. But I surely could not have gotten 700 nodes. And they wouldn't have given me 700 nodes, you know, even if you space it out. So we really calculated something that I couldn't have calculated with direct sampling. This is a wonderful quote from Newton. The planets move one in the same way in orbs concentric. Some inconsiderable irregularities accepted which may have arisen from the mutual actions of comets and planets on one another, and which will be apt to increase till this system wants a reformation. So Newton was very smart and was recognizing that there is a many-body problem where orbiting bodies can become increasingly chaotic in their orbits. And it's apt to increase. It's going to get more and more chaotic. The orbits are going to get increasingly out of whack until the system wants a reformation. And Newton's idea was that the hand of God extends to put the planets back into their orbits periodically. It gets a little bit eccentric, and then the system is stabilized. Which is totally amazing. This recognition, this early recognition back in the 1700s about instabilities. And then this idea for how stability is in fact reimposed in the system. Now, we were interested in studying the most likely instability in the future of our solar system, which is the planet Mercury. There is some possibility that Mercury in between 2 and 5 gigayears, 2 and 5 billion years, is going to get so eccentric, so ovally in its orbit, that it has a close encounter with the planet Venus. At which point, it's either going to hit Venus or hit the sun. It could potentially get ejected from the solar system, but it's more likely really to hit Venus than anything else in the simulations that we've seen. You don't have to worry about it for your grandkids or great-grandkids. They're probably going to be okay. All right? However, why do we care? Why do we care? We care, I care, because I care about aliens. I am interested in statistically how many aliens are there in the universe. And there are statistically fewer aliens if planets are often crashing into each other. It is going to disrupt the climates of all sorts of exoplanets. It's going to be harder for life to build up slowly. And I was just talking to my collaborators about this morning. Apparently, the moon is evidence of a Mars-sized planet hitting Earth. Do y'all know about this? This is so incredible. This is so incredible. So, you know, we're in the stable part of our solar system's evolution. We're pretty old solar system. We're pretty stable. You know, I'm telling you, there's a 4 in 10,000 chance that Mercury is going to have this close encounter with Venus that destabilizes the solar system in the next 2.4 billion years. So it's not too big of a worry, but it is important to estimate these probabilities to know exactly how frequently such events might occur. As our reaction coordinate, we used a 0.4 gigayear range in the Mercury-Venus minimum orbit intersection distance. We achieved a 10 to 30 times speed up over direct sampling. And we were able to do this with a pretty realistic model. This was a 4th order symplectic integrator called WACL with corrections due to general relativity. It turns out general relativity is pretty important. It actually saves us from these planetary collisions. Without general relativity, Mercury would hit Venus pretty regularly. General relativity saves our butts.
So general relativity is the hand of God.
Ah, there you go, sir. Yes, yes, yes. The hand of God is general relativity. This is some output from the model, which shows in astronomical units the 8 planets. There are 8 planets nowadays. That is the decision made by this particular software, the Rebound software, the Rebound many-body code in Python. There's fabulous New York Times articles debating the number of planets. But 8 is the decision made by the software. We added 1 centimeter random perturbations to Mercury's position every 200 million years. And this could model an asteroid hitting Mercury, for example. Random shocks that the model does not resolve. We simulated 1,008 samples for 2.4 gigayears. It required a week of runtime, but it didn't take a whole node, it just took 1 core. And I think we were doing it on nodes that had about 30 cores per node. So we were running it for a long time, but thankfully we were able to use this parallelism. Ongoing challenges, last part of the talk. Quantile DMC has surely made rare event sampling more correct. But there are still challenges. And I just want to be honest about this. It's still hard to find an appropriate reaction coordinate. And it's still hard to quantify uncertainty afterward. So, I don't want to just say that my technique is great. I want to say that my technique has improved mainly in the simplicity of the parameter tuning compared to things that existed previously. We've extended it to some of the most high resolution models that have been used with rare event sampling. But there's still challenges when you seek to extend this method further. Now, we use the 0.4 gigayear range in Mercury-Venus minimum orbit intersection distance as a reaction coordinate. And why do we do that? How did we come up with that? I can barely say it. It's really a mouthful. One has to find a reaction coordinate, and we came up with this crazy one. We tried to do the direct thing. We tried to look at Mercury's eccentricity directly because, Mercury's eccentricity is the y-axis in every plot that you ever see in papers of the evolution toward instability. Results weren't so great. We found that our error bars were too big, that our method wasn't quite giving us the rare events that we wanted to capture. Then what we had to do, which we're deciding now is a pretty good technique, it's something we would recommend, is to use sparse linear regression to select which variable to use from a bunch of contender variables. You have to do some pilot runs and then look at some contender prediction variables and do sparse linear regression just to pick 1 or 2 of them that work the best. And so, we predicted log instability probability divided by 1 minus p. This is the log odds ratio of the event occurring or not. And we got that there's a pretty big coefficient on the Moid range. Here, x means range. And it's like a 0.4 gigayear range. What's the maximum value over that period? What's the minimum value over that period? So it literally means that the orbit is getting really moved around a lot. And sometimes it's coming quite close to the Venus orbit, and sometimes it's far away. It's getting kind of stochastically pushed back and forth. And this is the best predictor of growing instability in the system, which will lead to a close encounter that we have so far found. We need reliable protocols to build better reaction coordinates as we generate data. I'm giving a mild endorsement of sparse regression as a way to do this, but I'm not really sure. Perhaps there's better ways to iteratively refine your reaction coordinates as you go along. To trust rare event sampling, we need error bars. You can say that you computed some probability and put it in a paper, but why should people trust you? Hopefully you're thoughtful about such questions, about what are the sources of error, what are the failure modes. We developed, based on mathematical analysis, an optimistic and a pessimistic variance estimator, and we applied them. So This is a figure that shows the QDMC instability probability calculated with either these thick optimistic error bars, which are really small, which are saying that our results are great, or these thin pessimistic error bars, which say, okay, well, maybe our method wasn't so good. Now, I have mathematically proved that the pessimistic error bars are biased too high for your actual variance. And then empirically, we find that these optimistic error bars are biased too low for your variance. And specifically, you know, for folks that want the gritty details, the optimistic error bars, what you're doing is you're treating each sample as independent at the final time. And you're just looking at a sample covariance over the particular weight associated with the simulation and the function you're trying to evaluate. So it's like saying there's no real correlation between these samples. They're all just providing independent data. And that's wrong. I mean, you know, they're kind of correlated, right? They have some shared ancestry. So this gives you error bars that are too small. But the pessimistic one, what that does is it traces back the ancestral history to who was the original Adam or Eve for that family. And then it says, okay, this whole family is one data point. This whole family might be so correlated that I just trust it as a single data point and no more. And that's too much. I mean, you know, things do decorrelate over time, right? So this gives you the pessimistic error bars that are, you know, too high. We need to develop more precise error bars. And I'm working on this problem. I'm trying to figure out, you know, when are the thick ones right? When are the thin ones right? And to close, I just want to say that quantile DMC has made rare event sampling more practical. It really has. There's major challenges that remain, but we believe with continued research, this approach will usher in a new standard for rare probability calculation in the Earth and planetary sciences. And I want to thank you so much for your attention and ask for questions. Does anybody have any questions? Yes.
I hate to dwell on the physics, but presumably you looked into this a little bit before you did your Mercury simulation. A centimeter variation in the orbit every billion years or so seems awfully precise orbits to me. I wonder whether the solar wind isn't just pushing Mercury around more than that. And the second part of the question is, did you or should you have applied perturbations to Venus as well?
Well, there's a couple answers to that. I actually think about these things sometimes and talk about them with, you know, my collaborators on this project. One answer is we don't really know where Mercury is to any more than a meter accuracy, right? So one could think of a different sort of uncertainty, which is based on our knowledge. You know, it could be representing a range of possibilities. If you do that, you'd have to put plus or minus 1 meter error bars on where Mercury happens to locate right now. 1 centimeter seemed to us to be reasonable, but we also did sensitivity studies where we tried smaller perturbations, we tried bigger perturbations, and it didn't make much of a difference. It was remarkably robust to the size of the perturbations. We never perturbed other planets though. That we never did. We have smaller perturbations by about 3 orders of magnitude compared to the first studies that ever showed that Mercury might have a close encounter with Venus. And you know, there's many reasons those older studies weren't quite as accurate as the one that I'm presenting here. In particular, I mean, some of them didn't include general relativity, which completely changes the statistics, right? So, you know, we felt like we were making some progress. We also felt like it didn't matter with Mercury, but we did not address the question of what would happen if you also perturb Venus. You know, is that a complete answer?
Yeah.
Cool, yeah. My hunch, for what it's worth, is that a lot of small random perturbations lead to pretty similar statistics. But we've not totally proved this. We've only created plots that show what happens if you do a centimeter, a millimeter, a meter, 10 meters for Mercury. Yeah. Yes, Maddie.
Again, piggybacking on Steve's question.
Yeah.
In your list of challenges, wouldn't be the random perturbations also be a challenge? Because in the well, I don't know what happened in the first example, but in your Wharf model, you just switched on some random perturbation within the Wharf. And this one you have well, you explained that you kind of carefully chose it, but I would think that maybe the random perturbations that you use do have a big effect, but you were just arguing that they don't. Is that right? Because in your list of challenges is reaction coordinates and error bars. Why is there not the random kicks that you need every so often? You think it's really irrelevant how you?
No, I don't think it's really irrelevant. There's several schemes for Wharf that give you stochastic weather. And I picked the one that I thought had the best track record. I mean, it's been developed pretty seriously by folks at NCAR, who are also the developers of the Wharf model. You know, I mean, they have a slight bias towards reproducing the weather over the Atlantic really well, more so than the Pacific. You know, you'd expect as much. But, you know, they tuned this one pretty thoughtfully. And so I was pretty happy that they'd already done it. But you look in this literature and they've got the SCAB scheme and they've got some other alternatives. And indeed, they're showing that, you know, there can be some differences depending on what you do.
But for the one-time DMC, it wasn't critical, which stochastic scheme you picked.
Well, we only did it with one stochastic scheme. So we picked the one with the best track record of success. I guess, like, whose challenges are these? I mean, are they the challenges for the model developers? Are they the challenges for me and my co-authors? I was mainly thinking, you know, about the challenges for me and the co-authors, because the basic principle behind all of this is you have a model that you trust, but you just need more information from it. You just need to run it more computationally well. All of this fails if you don't have a model that you trust. And in fact, to be honest, what we're currently doing is we're going back into Mercury. We're like almost doing a repeat study with an even smaller time step. And we're creating an ensemble of like 5,000 different runs of 5 billion years into the future for the whole solar system using this really good time step. You know, so I kind of always will have to have some subject area specialist who knows a lot about this, who has a cool model they trust. Yeah. Yes.
It could be that with these sorts of like climate models and such, that all you need is just a very small perturbation to get just differentiation among the children, so they go in different directions as opposed to being the same deterministic run. And that the size of the perturbation you make isn't actually that important, sort of the butterfly effect. As long as there's even the tiniest of difference, you'll get splitting. But it doesn't matter if that perturbation is, you know, really small or just really small.
My rough impression is that the precise nature of the perturbation matters a lot more for the Wharf weather models than for the solar system evolutions. The solar system evolutions, there seems to be this crazy Lyapunov timescale that's super short, which blows up any like really tiny perturbation. And it does so in a relatively predictable way, despite the precise nature of that perturbation. That's my impression. Whereas, you know, there's more systematic differences with these weather models, depending on which fields you perturb, for example. You know, so obviously, like, right, they had to be careful, right? They're not creating divergent or convergent winds, right? They're working with the non-divergent part of the wind field, for example. And I'm so glad they did this work. Yeah. Yeah, it was good. We just copied the physics schemes from a paper that came out of INCAR, actually. Because we thought that, okay, these are folks that really know how to simulate this hurricane. So we're going to use their physics parameterizations. Yeah. Yes, Kathy.
So if I decided that geomagnetic reversals were rare events.
Yeah.
And I wanted to figure out what the reaction coordinate was, what would I need to do?
Well, yeah, I would argue that you would want a data set at this point. And you would want some potential predictor variables. And you would probably want to do a sparse linear regression to figure out which one's the best. And that at this point of development, to be honest, short that data, you know, you probably wouldn't be able to apply these techniques yet.
But I could do it on a numerical simulation.
Yes, of course.
I felt like it. So then you would have to do something like what you've done it here. Where
Yeah.
you would introduce some kind of ensemble process to the numerical simulation, which nobody likes to do in that world.
Oh,
Because it's too expensive.
yeah, that does make sense. I hope that this talk gave an idea of the number of ensemble members you have to afford for these techniques to be useful. And the answer is roughly, I wouldn't advise them if you can't afford 100, but you'll get better results if you can afford 1,000. And so that's also an unfortunate reality of these methods. Yeah. Yes.
I have a related question.
Yes.
I don't think I fully understand
Hmm.
what the role of the reaction coordinate is. And so I was hoping you could describe, I mean, the key part of the decision rule, I mean, when you branch, when you kill.
Yeah, for sure.
Where is it, how does this actually form a decision? Can you go more into detail on that?
Yeah, sure. Sure. Okay. So importance weights are a way to sample more some members of a discrete set on average than other members of that discrete set. And so I'm particularly dealing with unnormalized probability importance weights, which means they don't have to sum to 1, okay? They don't have to sum to 1, but the ratios are going to be super important. So if IK1 and IK2 are related in that IK1 is the highest value, it's 10, and IK2 is also pretty high, but it's like 5. And this is averaging so that all of them sum up to the ensemble size, which is 512. On average, the first guy will have 10 children. The second person will have 5 children. So these importance weights are the expected number of children. Now, importance weights are related to the reaction coordinate directly at time 1, but somewhat indirectly at the subsequent times, in that it's ratios. So this kind of makes sense. I mean, in terms of progress, right? Like you've already progressed to a certain level, and you're not progressing beyond that. You know, have you really survival of the fittest? Like, have you really made it any further? Do you really deserve any more offspring in this game? Potentially not. I mean, you need to make more progress, and then you get the more children. If you make less progress, if your ratio is less than 1 after normalization, then you are going to statistically die with some probability that's 1 minus your importance weight.
So the, that's the reaction coordinate, it actually informs the update of the importance weights, or?
Yeah, yeah, that's right. Yeah. So reaction coordinate implies importance weights, implies splitting and killing.
Okay.
Yeah.
I don't want to just try to shoehorn this all into sequential importance sampling, but this is so similar. I feel like there are some really nice connections. I'd be very curious. I mean, if you explored it through that framework a little bit. I mean, if yeah, there'd be other extensions that you could have with this type of algorithm to, sequentially update based on new observations, things like this.
Yeah, I think that is a clear connection. With the proofs, I even use some of that literature,
Yeah.
right? So, you know, Del Moral's got some martingale-based analysis.
Yeah.
And that's a basic building block in what we do as well. And I would position this work potentially as a particular example of sequential importance sampling that has a lot of parameter decisions that have been really tried and tested and are pretty simple compared to the other available solutions in the literature. So I would position this as an attempt to make that literature more practical and more impactful. Yeah.
Cool, thank you for the clarifications.
Yeah. I mean, you're right. Yeah, is this just sequential importance sampling? Sure, it is. It is. But, you
It's
know.
an interesting, yeah, it's a nice choice.
With a lot of specifics thrown in, and those took a lot of time to develop. So,
Sure.
yeah. Any other questions?
I think Peter Shearer has a question.
Oh, fabulous. Let's hear it.
As I understand it, the method depends upon having the reaction coordinate that's a measure of how progress toward the rare event. And I'm wondering if there are models that are so chaotic, behave so chaotically that in some sense you don't know that you're close to the rare event until it happens. So it would be hard to use these methods on, I guess.
Yeah, that's a beautiful explanation, and it's totally correct. So planetary dynamics has a Lyapunov timescale that's pretty short. And you can kind of see it when you look at our plots. You have to look really hard. But for example, you can see here, one trajectory is being split into like 20 or 30 offspring. They are the same for a while, and then they start to spread out. What's being hidden by this plot, though, is this is just one coordinate. This is the Mercury eccentricity, but there's all sorts of other information that's decorrelating much, much more quickly, that is much, much less predictable. So for example, the orbit could be thought of as a donut. And where are you in the donut? Are you at 3 o'clock? Are you at 9 o'clock? Are you at 11 o'clock? That is a quantity that is patently unpredictable. That one decorrelates much, much more quickly, and you would not be able to succeed in rare event sampling for where precisely in the donut is Mercury at some point 2.5 billion years into the future. If someone does it, if someone implements that and figures it out, then I'd be incredibly surprised, but I think it's undoable. Yet, I would argue that this is kind of proof that just having a really short Lyapunov timescale for some aspect of planetary motion doesn't mean that you have a short Lyapunov timescale for every aspect of planetary motion. And isn't it remarkable that no one with the modern models has ever simulated a Mercury instability event within 1 gigayear? So there must be some memory that's at least 1 gigayear, at least on the order of 1 gigayear. So maybe more stuff is predictable than we might think on the surface. And surely it has to be evaluated for every single rare event differently. So I think it's a beautiful comment, and it's right. The limits of applicability are totally, totally chaotic stuff we can't predict at all. That's right, yeah.
But we are past the canonical hour, so let's thank Rob one more time.
Thanks, guys.
And thank everyone for joining. We'll see you next week.
Awesome.